Great. So thanks for the lovely introduction. It's a real pleasure to be talking to people at the GRASP Lab, and it would be wonderful to come down and visit at some point in person. So this talk is called Towards Complex Language in Partially Observed Environments. So what my group thinks about is big, complicated robots that are operating in complicated environments. So during my talk, I was working on this forklift project that's an autonomous robot that drives around in warehouse environments and can autonomously pick up pallets and move them around to different places in the environment. Today we have self-driving cars from companies like Waymo and Cruise that are getting closer and closer to the ability to pick up passengers and really operate without a human in the driver's seat. There's been a revolution in autonomous drones. So we were just playing with the Skydio 2 autonomous drone that can fly around and avoid obstacles for $1,000. Take really cool shots of from the air. And at Brown, we're teaching a class where every student gets their own autonomous drone, where all the parts are off-the-shelf parts, and all the autonomy runs on board the drone implemented in the Python programming languages. So this makes it really easy to sort of hand everybody in the class a robot, all the parts for a robot, and they put together and they make it fly. So this technology is becoming democratized. It's really accessible to a really broad spectrum of people. So as robots kind of move into our daily lives, there's a question of how are we going to tell the robots what to do? So if you look at existing interfaces, this is a picture from the forklift project, and people were using a touchscreen interface to sort of tell the robot what to do. And that's the same today. So like if you get in the back of a Waymo self-driving car, there's a screen that sort of lets you see what the robot's seeing and control, what it's doing, give it destinations and stuff like that. If you fly a Skydio drone, you install an app on your phone, and then you use that app to make it so that the robot, tells it where to fly and stuff. So the problem with these interfaces is that the user's hands and eyes are down in the interface rather than out in the world where the robot is and where all the good stuff is. So instead, what my lab is thinking about is trying to make a robot that can collaborate with a person just as if it was another person. So you say to the robot in words something like, put the metal crate on the truck. And then the robot has to figure out what the mapping is between words like metal crate and a really high dimensional stream of data coming from its sensors. It's challenging because people don't always stick to a fixed vocabulary and grammar. So this is showing the forklift doing a quick little video, a quick little action. And what we do, and this is like sort of underlying all of our data collection for all of our papers, is we show them some representation of what the robot's doing. And then we ask a person to say, how would you give a natural language command to this robot as if you were talking to a person to get them to do this action that you see here? So people say things like, put the tire pallet on the trailer, or place the pallet of tires on the left side of the trailer, or lift tire pallet, move to an occupied location on truck, lower tire pallet, reverse to starting location, lower forks, and they kind of made up this programming language that they want the robot to understand. So the challenge is when we do this, even for this really short little video, people don't stick to this same vocabulary and grammar, and they say things in all kinds of different ways. So when we look at all the different things that people said when we showed them this video, I should just admit a person. Somebody admitted that. Yay. Yeah. Thanks. So no two people gave the same command twice, even for that very short little video. There's just a tremendous amount of diversity in the ways people choose to formulate things with language. And of course, we don't just want to put, the metal crate on the truck. You might want to give really fine-grained commands to a robot, like move backwards 10 feet, or really high-level commands to go off and operate autonomously for a long time, like move everything from receiving to storage. And we also don't want to assume everything is going to work all the time. So if you say, put the metal crate on the truck and the robot gets confused, we'd like it to do something like ask a question and say, which truck? And then the person might give an answer that sort of clarifies what's going on. So the fundamental challenge in this problem is that people want to talk to robots about everything they can see and everything they can do. Everything. So we need a model of everything the robot can see and everything the robot can do. So what my group is thinking about is creating decision theoretic models for communication, action, and perception. We need models for communication because that's what language is about. The models for action that's getting at everything the robot can do. We need to represent really high-level abstract actions and also really fine-grained low-level actions. And we also need models for perception because we don't just want to assume that the sort of perception robotics people have just solved this problem, because language and perception are intimately tied together. So to see this, imagine that you tell a robot something like, pick up the speck of dust on the ground. Robot, go pick up the speck of dust and throw it away. Before I said that to the robot, it really had better not be paying attention to all of the specks of dust in the entire environment. But after I say that, if I want the robot to understand, it better somehow have dreamed up a speck of dust detector, localized that speck of dust, and then made plans involving that speck of dust. So you can see that depending on the goal that the robot has, the perception system needs to be tuned and needs to sort of decide what to pay attention to so that it can achieve the goal. So if we make this work, by learning these models, the robot's going to be able to scale to very large problems. Because they're decision theoretic models, which represent the robot's goal and not just its plan for achieving the goal, it should be able to detect and then recover from failures to understand, either physically by trying a different physical plan or socially by asking questions using dialogue. And last, by combining these abilities together, the robot will be able to improve from experience, get better over time as it collects more data about the person and about what words mean. So the overarching technical framework that we're using to address this problem is that of partially observable Markov decision processes, or POMDPs. So a POMDP is represented as a sequence of states where each state depends only on the previous state, the one that was right before. And you can think of the state as representing everything that there is to know about the physical world, like where the robot is and where its joints are and where all the objects are that it might want to do stuff with. At each state, we get an observation. So depending on where the robot is in the environment, its LiDAR sensor is going to give a different reading. And this observation depends only on where you are right now, not where you used to be. This is the Markov property. Because we're talking about a robot, we don't just get to observe the states and the observations. The robot also gets to take actions. So each action affects, depending on what action the robot takes, affects what happens in the next state. So if the robot chooses to drive forward a little bit in state t-1, then in state t, you can expect that its x-coordinate will have increased because of that action. And last, we need some representation of what the robot's goals are. And that is the sort of reward function. So this is a number that's assigned to each state that corresponds to how good it is to be in that state. So solving a POMDP corresponds to finding a mapping from belief states to actions that maximizes your reward over time. So solving POMDPs in general is extremely hard. And some people get turned off by these models because they're so hard to solve in the general case. But we shouldn't be surprised that the model that we were looking at to sort of make robots understand language is hard, because robotics is hard and language is hard, and robotics and language together is even more hard. So we need a powerful model that is capable of representing everything the robot can see and everything the robot can do. And in fact, POMDPs are the simplest model I know of that capture observations, that is what the robot can see, and actions, that is what the robot can do, and combine them together. So what we're going to do, what the name of the game is to take this sort of general framework and find representations, independence assumptions, and tricks that enable efficient learning and inference in this framework. So what we're working towards is something I call the human-robot collaborative POMDP, where we make assumptions about how the world works and how people work in the world with the robot in order to enable the robot to collaborate with people. So the first thing we're going to do is factor the state into two components: the physical state of the world, which again is like where the robot is and where the objects are, and then also the human's mental state. And this is very simply what the human wants the robot to do. So then we can sort of say, okay, we want to know what the robot's reward, the goal, is to do what the person wants. But the problem, of course, is you don't know what the person wants. It's not observed, right? You only get to observe your observations. So then the challenge is to look at our observations. So we have our physical sensors, like our LiDAR and our camera. We have a microphone, and we can run a speech recognition system on it. We can get a language signal. We can use our camera and run a body tracker or body pose estimator on it and get the person's gesture. And now the goal is to look at this noisy stream of sensor information and estimate the person's mental state. What do they want us to do? And then go and do it. So if you're looking at the language, what the person's saying, and trying to estimate their mental state, this is the problem of language understanding. You can also imagine taking actions that change the physical state of the world, for example, driving forward or picking something up, but also social actions that are aimed to change the human's mental state. So if I ask the question, if the robot asks a question, then it might do that because it expects that this will change the person's mental state so that they'll know what the robot needs, and they'll be able to answer the question or provide help to the robot. So this is the problem of communication. So figuring all this out and how this works is the problem of communication for collaboration. Then you can sort of think about the physical state of the world and how the robot's physical actions change that physical state over time. And what we're going to see is that we're going to need a very rich representation for actions that handles both very low-level, fine-grained actions as well as very high-level abstract actions. And this is sort of figuring out how to represent this is what I call action for collaboration. And then last, we're going to think about the sensors. And this is going to get at questions like the speck of dust problem. You know, how do I make my perceptual system so that I can tell the robot, pick up the speck of dust, and it can tune its perceptual system to pay attention to the specks of dust while it's doing that action, but then stop paying attention at other times so that it doesn't get overwhelmed by all of the objects, all of the things in the world that might matter sometimes. And that's what I call perception for collaboration. So this is sort of a really big general framework, but it sort of informs how our group is thinking about these problems. So now I'm going to go dig into some specific papers and projects that we're doing that sort of show how this plays out in practice. So the first thing we're going to think about the problem of understanding natural language at different levels of abstraction. So we want to understand really high-level commands like move everything from receiving to storage, but also really fine-grained commands like move backwards a little tiny bit in the same model. So to study this problem, we're going to look at a simpler simulated environment where the robot is in a kind of grid world where there's objects in the world and the robot can push around different objects. And there's rooms and the rooms have different colors. So you might say something to the robot like take the red chair to the blue room as kind of a high level command. But you also might say a low level command like go down 5, right 5, 1 up, right 4, down 1, left 1, and up 3. Now, as it happens, these both result in the same thing. If you do the thing on the left, it results in the red chair being in the blue room. And the thing to sort of realize is that we don't just want one of these levels of abstraction. So if you're only using low-level instructions like the go down 1 and stuff like that, and then you go to a really large environment. So this example is the International Space Station, but you can imagine other large environments as well. It's going to get really old really fast if you can only say these really low-level things. But if you can only understand the high-level instructions, then you can't give the robot these sort of fine-grained corrections. You can't say like go down 1 and west 1 so that the robot's in the corner. You just don't have the granularity. Sorry, somebody came in the room. I got a little message. So you want to be able to understand both. So what we did to address this problem is we built on some prior work that represents language, that represents the human's mental state and here we're going to use mental state and the reward function interchangeably. So we're going to represent the reward function given a natural language command and use the IBM Model 2 language model to learn how to do this mapping from English to reward function. You just argmax over different reward functions and find the one that is most likely according to language. So what we did is replaced the sort of single level representation of the reward function with hierarchical abstraction. So you could say the reward function as well as, it would basically estimate the reward function as well as level of abstraction. And then we upgraded the language model to be neural networks because they work better and they're the current fashion. And we showed that using this framework, we're able to understand these kinds of commands that are given at different levels. So going back to the POMDP model, you can see that the action space is now being represented hierarchically because we're representing these different levels of abstraction and then giving the language model a way to hook into those levels of abstraction.
Go to the red room.
So here's what it looks like. The student says, go to the red room. And here the rooms are the colors of tape on the ground. And then the robot's able to follow the command.
Go south, south, south.
Or the person can say go south, south, south. So this is the sort of same thing at a lower level. The same model and no changes. You're able to understand these sort of different levels of abstraction. And because it's using a planner, if something goes wrong in the process, if you block the robot or pull it into a different room, it's able to efficiently replan and recover if there's some kind of failure. So that's hierarchical commands. But there's also other sort of kinds of language and other more complicated expressions that we'd like to understand. So one example of that is what we call non-Markov commands. So you might want to say to the robot something like go through the yellow room to the blue room, kind of very natural thing to say. You know, go down the hall and then turn left and then be in the living room. The challenge with these commands is that when you're using a planning based representation where you're representing the goal, and you're using a Markov representation where you only get to see the current state, you can't tell the trajectory that a robot followed to get to end location. So you can't reward the robot for going through the yellow room once the trajectory is done, because you only get to see where you are right now. You only see now I'm in the blue room, and not how did the robot get to the blue room. If you could see that, that would be breaking the Markov assumption that things only depend on the current state. Now, we could extend the state space so that the robot stores the entire history of where it's been and then puts that into its reward function. But then the planning problem gets really big, because we've just increased the size of the state space, and that makes it really hard to find trajectories in the environment. So to address this problem, we turn to something called linear temporal logic, or LTL. So LTL is a representation for having logical reasoning over sequences of states. So not just the current state that you're in, but a sequence of states. So for example, you can have it has these sort of temporal operators like finally P. So it means that eventually at the end of the sequence, this proposition has to be true. Or globally P, which means this proposition P has to be true through the entire sequence of states. Or next P means that the proposition has to be true in the next state that I'm in from where I am right now. Or P until Q means this proposition has to be true until this other proposition is true, and then it can stop. P and Q both don't have to be true anymore. So this is used in the programming languages community for model checking, and it's being used more and more in robotics because of its ability to represent these kinds of constraints. So what our approach was using LTL is to represent this problem with a Markov decision process, an MDP, with propositional functions like whether or not I'm in the blue room. And we called this the environment MDP. And then we're going to skip to this bit and then go back to the data. And then we take the LTL expression and you convert that to a finite state automaton. And this is kind of a thing, like every LTL expression has an automata representation that goes along with it. And then we take that finite state machine and connect it up with the environment MDP, so that we get this larger MDP with some extra states in it that correspond to the LTL expression. So then what we could do is solve that kind of merged MDP that has these extra states. And what the extra states do is they save just enough extra information about the robot's history so that the LTL expression can be evaluated, but no more. So for example, if you tell the robot to go through the yellow room to the green room, it's saving just one little bit that says, have I ever been in the yellow room, yes or no? And that way, it's possible to evaluate just this natural language expression without having to add the entire history of states. So then we collected a data set where we showed people trajectories of the robot doing things in this little environment, positive and negative examples. And then with each set of examples, we had an associated LTL expression that we annotated. So in this case, in this example, sort of the green trajectory is the positive example, the red trajectory is the negative example. And then people would say things like go to the green room or go into the red room, enter the blue room via the green room, go to the blue room but avoid the red room. These are all different commands that correspond to different LTL expressions. So we collected about 800 commands, which was the largest corpus that we're aware of English sentences that map to LTL expressions. It was challenging to collect this data. So obviously we can't have annotators on Amazon Mechanical Turk directly write down LTL expressions. So we had this thing where we showed them these examples. But what we found is that the annotators preferred to specify positive rather than negative behavior. So if our LTL expression was go to the green room and avoid the yellow room, instead the annotators like to say go to the green room through the blue room. They like to say the positive thing instead of the negative thing. They're both correct in the sense that they match the examples we're showing them, but they're different LTL expressions. So we had to go back and manually relabel the LTL expressions when this happened, so that it corresponded to the words that they were actually saying. And we also did some hacks to expand the data set to swap color words around so that our neural model was able to learn things without prejudice to like what colors it happened to see in training. So for example, like if it saw go to the red room, we also wanted it to see go to the blue room. And then we used a seek-to-seek model, a neural seek-to-seek model to learn to go from English sentences to LTL expressions. And then once you go from English to LTL, you can do this thing of converting the LTL to a finite state machine, and then combining it at high speed with the underlying environment MDP, and get an overall MDP that you can then solve to find a policy. So what we found was that our neural models were able to learn, this is showing on the right here, a graph of the performance of the neural model as you increase the number of commands seen at training. And as we increase the number of commands, the model is getting better and better. But sort of our best performing variant of the model is just under 60% performance, which frankly sucks. You know, it's good, it's doing something, it's learning something. But it's going to be wrong, you know, almost half the time. And the other thing to note about this is that as we increase the amount of data, we're nowhere close to asymptoting off. The model is still very rapidly getting better as we add more data to the system. So although this is progress, this was the largest corpus to date of English to LTL, we really haven't scratched the surface in terms of how much data you need. There's more to do. And I'll talk about another paper that we wrote after this to address this problem. But that said, it does, you know, it does work when it works. So you can sort of say things like go through the blue room to the yellow room, and it generates the LTL expression and then is able to find a trajectory that corresponds to that. So here's a video showing what it looks like when this works.
Go to the blue room.
Again, the room is the walls.
Avoid the green room and go to the blue room. Go through the yellow room to the blue room.
Turning very slowly. So you can kind of give these variants of natural language instructions and generate an LTL expression, and then the robot's able to. So I'll stop it there. So we also, you know, so we wanted the ability to understand LTL expressions and abstraction at the same time. So it turns out to be not completely straightforward to do that. So we had another paper that combined these two capabilities so that we could both reason about abstraction as well as incorporating these temporal commands. I'm going to skip that one. So we sort of made a lot of progress in the robot's ability to interpret commands with a powerful semantic representation in LTL to kind of capture means. But we're still working in these grid world toy environments. So what we wanted was sort of imagine a drone that we unbox and take it to, you know, wherever you happen to be, and be able to give that drone natural language instructions. The challenge with this is that there's lots of really weird landmarks out there. So this was a sculpture that was at Brown for a while. They've since removed it, called Bluno. And yes, the lamp does go through the head. And what this is a really wonderful landmark. If you tell somebody, if you tell a person, I'll meet you at the Big Blue Bear, it's really unmistakable exactly what you mean. It's a wonderful landmark. But it's also, and it kind of, this goes with it being unmistakable, it's unusual, it's surprising. It's never going to be in your training set unless you happen to have already trained, collected data at Brown with this statue. So the challenge is how can we understand commands like fly to the Big Blue Bear when the robot hasn't seen the Big Blue Bear ever during training. So what we noticed is that even though this doesn't appear in the training set, it does show up in maps of the environment. So a lot of these landmarks are distinctive and permanent, and they're in the OpenStreetMap view of the environment. So sort of information about it and keywords and some idea of what it looks like. So the challenge is how can we take our model that with LTL, which kind of has to have pre-specified predicates that have to have been seen at training time, and generalize it so that you can understand something like fly to the Big Blue Bear when you've never seen it, the words Big Blue Bear or the object Big Blue Bear during training. So what we used is to solve this problem is a natural language, a technique from the NLP community called CopyNet, where if you say something like go to the medicine store, the CopyNet model will take the sentence and extract LTL, but recognize that the phrase the medicine store is a landmark, a noun phrase, and pull it out of the sentence in quotes. And then what you can do is take that and send it to a special module for resolving landmarks. So for this, in that module in general, it could be anything. It could be something that was deep learned. But for this model, for this paper, we just used cosine similarity with the OpenStreetMap data. So we vectorized both strings, and we vectorized all the landmarks. We vectorized the noun phrases and ran a search to figure out what landmark in the map, what grounded landmark the person was talking about. And then what this lets you do is take the model, which maybe was trained on data that was collected in Providence and in Boston, and then take it somewhere else. In this case, they took it to Tulsa, Oklahoma, in simulation. This was all during COVID, and there was no training data from this location at all, but the robot's able to understand commands because of the ability to extract the noun phrases and go from there. So this is sort of addressing the problem of handling out of domain, handling commands that refer to landmarks that you've never seen in training time. But the problem still, and I sort of alluded to this before, is that if you look at sort of existing work in robotics and NLP, almost all of it has some kind of parallel data set of human language paired with some kind of abstract meaning representation, robot-ese, the robot's language. And because of that, these data sets are necessarily very small, with hundreds or at most thousands of examples of English going to this abstract representation. If you compare this to existing work in NLP and machine translation, where you're looking at parallel corpora of human language pairs, there's really, really large data sets, and to the tune of millions of examples of sentences that are pairing two different human languages. The problem is that we're never going to get to that scale of amount of data in the robot setting because people don't know how to speak robot-ese. They don't know what representations for meaning we roboticists are using for our robots. And in fact, we roboticists don't even know. A lot of our research, a lot of the sort of two previous papers I was telling you about you can think of them as exploring different representations for meaning, and how those representations can connect to a planner so that the robot can go out and do stuff. So to address this problem, we decided to try to take as our model of the NLP community, where we looked at, this is sort of one particular sequence of papers from the NLP community using a data set called GeoQuery. And this is a data set of English sentences, English questions, paired with Prolog database queries. So queries like English sentences like, what states border Texas? And then associated with it, a database, a geographic database, and a Prolog query whose when you run it on the database would return the answer to the sentence. So the very first papers on this GeoQuery data set use training instances that consist of sentences paired with the parse tree. So a human had to actually parse manually the English sentence, give the parse tree to the model before it learned to parse it. Then in 2005, Luc Zettelmoyer's thesis was to say, actually, you know what? We don't need the parse tree. So we're only going to give it the English and the logical form, the semantic representation. We're not going to give it anything about the parse tree of the English. Then in 2009, Percy Liang and a couple other people that did similar things with this data set at the same time said, you know what, we don't even need the logical form. We don't need the semantic representation at all. All we need is the ability to know if our answer is correct. So we're going to provide the answer to the question without telling, and we need to know whether the answer is correct or not, but we're not going to have any logical forms during training time. And this is sort of the best because you need very little, you need less data, and you need no experts to annotate this data to make this happen. So if you compare this to our robotics work, where we're going from English to LTL, we're back at Zettelmoyer and Collins. We're able to go from English to a formal representation, but to do that, we need a data set of English sentences paired with our LTL representations. To go to that next level, where we don't need LTL at training time, we need a more sophisticated model. So we did this by making a model that goes from English sentences to LTL with no LTL needed during the training process. So what this means is the model is capable of learning during a training process where it only sees trajectories. So we're showing it positive and negative examples of trajectories in the environment. And we show our truckers these examples, and they give us natural language instructions. But we don't need to give them any LTL during training. It's able to infer the LTL. So at the end of the training process, the robot has both annotated the training set with LTL expressions, as well as have the ability to go from English sentences to logical form sort of at test time. So we're super excited about this work. It was published at RSS last year, and it's going to enable us to scale up the size of our data set by going to Turkers and collecting much larger data sets. We don't have to annotate the trajectories. Okay, just checking the time. Okay. So sort of coming back to this POMDP framework, what we're exploring is more and more sophisticated representations for human mental state that incorporate abstraction and models of linear temporal logic. So the last thing I want to talk about is models for perception. So we're thinking a lot in my lab about this problem of finding objects. So you might say to a robot, find the screwdriver, it's in the toolbox. or a ground robot, you might say, find the mugs in the library, the living room, or the kitchen. And what we want is for the robot to have the ability to take as input this language and then update a model of where the objects are in the environment, and then go and search for the object. So using its sensor. And its sensor probably has a limited range and a limited field of view. So you want to sort of be able to combine information from multiple different sources. So for example, if you say something like this, find the mugs in the library, living room, or kitchen, here we're showing the belief state of the robot where darker blue is less likely, lighter blue is more likely. So when you give the language, it kind of makes those rooms more likely. So then the robot starts driving around and using its sensor. And as it uses its sensor and sort of calls its sensor information, then it does a belief update based on not seeing the object, and then turns around and then does detect the object. And so everything else gets really less likely, while the detected location of the object is really likely. This is sort of like a representation for planning under uncertainty that captures object search in a really natural way. But the challenge is sort of goes back to POMDPs are really hard to solve. So you want this kind of representation, but if you just write it down as a POMDP, you're never going to be able to find a policy like the one that you see being executed here, because the state space is so large. So planning is really difficult. So what we did is created a new kind of representation for POMDPs for this problem. We introduced the concept of object-oriented POMDPs, OO-POMDPs, where we factored the state space of the world in terms of objects. And then we showed that using this kind of representation, we can derive an associated new inference algorithm. So POMCP is the state-of-the-art algorithm. We derived object-oriented POMCP, OO-POMCP, which is a variant that exploits this factorization to get faster inference. What that lets us do, that representation, lets us achieve the behavior that, like you're seeing in this example, where the robot's able to efficiently incorporate information from multiple different modalities, from language as well as from its lower level sensors, to make a plan to find an object in the environment. So that's kind of an example. We also did a quantitative evaluation where we compared the performance of different variants of OO-POMCP, as well as a random algorithm, POMCP, and a sort of perfect algorithm that sort of has full information. And what you can see, the thing to look at is the graph on the far right, where what we tried is 4 different conditions. So the misinformed condition is where the language is actually lying to the robot. So we tell the robot, oh, it's in the kitchen, but actually it's not, the object is not in the kitchen, it's in the living room. Then the no information is where there's no information from language at all. So the person, they're not lying, but they're not helping you either. They're not telling you where the object actually is. Ambiguous is where the person tells you in language, it's in the kitchen or the living room. And it is, it's in one of those 2 rooms. But you don't know which of those 2 rooms it's in. And then last is the informed case, where you say, the person says, it's in the kitchen, and it really is in the kitchen. And then on the y-axis, we're showing the reward. And you basically get rewards for finding objects quickly. And what you kind of expect to happen is that you get more reward the more information you get from language. So the graphs are all kind of trending upwards. The more information you get from language, the more rewards you get. But if you look, the sort of worst performing algorithm is random, where you're just randomly wandering around the environment, hoping we find the object. Somewhat better is POMDP. So this was the previous state of the art. And then way better than that is the sort of variants of OO-POMDP. So we're just showing different versions with different parameter settings. And they're basically doing an order of magnitude better than the baseline, and that doesn't use this object-oriented abstraction. And then that dark blue line on the top is the fully observed baseline. So it's just to give an upper bound to kind of scale, give you a sense of scale for the reward section. So we're showing what happens if the robot knows where the object is for sure and just drives straight to it and finds it. So you can never beat that. But in the informed case, we're actually getting quite close to the performance of this baseline, which is kind of what you want because we're saying it's in the kitchen. So it's kind of more like when you know where things are. And if you're a Bayesian, if you're a POMDP person, you might be like, well, of course it's going to do this cool thing of like recovering from failure. If I lie to the robot, it goes to the kitchen. It's not in the kitchen. It looks all around the kitchen, and then it doesn't update. Oh, it must not be in the kitchen. And there's a smoothing term, and then it goes and looks everywhere else. So it takes longer. And if I tell the robot the truth, it takes shorter. But either way, it finds the object. This is sort of the beauty of what a Bayesian model, what a POMDP model can do. But the trick is that we're able to do it fast enough to be able to solve it in practice and get this really cool looking behavior. And since this time, we've actually extended this. This was in 2 dimensions. We extended this to 3 dimensions, and that was published at IROS last year. It actually won a RoboCup Best Paper for being able to use a 3-dimensional model with octotrees to help us factor the state space. And we made it run on a robot. I'm not going to show the video, but it runs on a robot. Okay, so we kind of changed our state representation to this factored representation. And then that enables the robot to efficiently incorporate information from language. And the work I was telling you about, we're using a really simple keyword model of language where it just knows words that go with different rooms. In a more recent paper, we're also incorporating information from spatial language. So you might say something like, find the car behind the building. And then the model does a belief update based on the word behind and grounding the landmark, and then finds the object with its detector, sort of doing this multimodal fusion. So that's sort of what we're thinking about as perception for collaboration. So we sort of started with this very simple, spare POMDP model with states, actions, rewards, and observations. And through the course of this talk, we've added a lot of stuff. We've added hierarchical abstraction. We've added models for objects. We've added rich representations for language. And we're sort of still on this road to try to make robust models for collaboration. So I'll stop there and take questions. And I'll leave you with another thing we did with written language, where the robot learned how to write. Thanks.
Okay, thank you very much. Anybody who's in the room, feel free to just ask questions. And anybody who's remote, feel free to unmute yourself to ask the question.
So I have a question.
Go ahead, George.
So thank you very much for the talk. This was very interesting. So my first question is, do you always assume that you have a map? And I'm talking specifically for the examples you are showing regarding the colored rooms, where you have the robot and you are asking it to go, let's say, to the blue room. Do you assume that there is a map of the environment and that the agent is aware of it?
Yeah, in that model, we assumed fully observed. So we assumed that the robot knew the colors of all the rooms as part of the underlying state space.
I see. So have you considered like the case specifically for that particular experiment where you don't have the map, but then the language itself can give you some information of what you can anticipate from where the robot is.
So, so what we're thinking about now is like a hybrid model where some of the landmarks are observed and you know where they are, and other landmarks are not, and you've got to go find them. So like the sort of use case is like the find the car behind the building, where the building is in the map. It's an OpenStreetMap. You can localize it, but the car isn't because it moves around and stuff. And then you have to be able to solve, and you might say stuff like find the car behind the building, but also, sorry, the baby's making noises. He's gonna go out to the lobby. So you might say things like find the car behind the building, and ground some of the landmarks in OpenStreetMap data, and other landmarks you've got to connect to your sensors and go and find them.
I see. Okay.
But I definitely think that like that pushing on that more is like the cutting edge for us, like trying to understand how to connect what you're saying with the perceptual system. And so we're also thinking about like trying to like create detectors from vision. So for example, if you say, the big red mug on the table, you'd like to be able to make a big red mug detector with your camera. And there is some work that does this, but the problem is with the existing work which is from the computer vision community, is that it's trained on a data set where you show it images with a big red mug, and then the words big red mug, and there's and then the big red mug is maxed out. But actually and so all the examples, there's a big red mug or whatever you're talking about somewhere in the image. And actually though, when you're using it for object search, most of the images that you're feeding to the algorithm are negative examples. Like there is no big red mug. There is no big red mug, and you need to know that, oh, it's not here, oh, it's not here, oh, it's not here. And so you get this problem with false positives where it hallucinates the big red mug when it's actually not present. And so we're thinking about ways to represent, to learn better models that are robust to this kind of problem. It's more like an information retrieval problem.
Right. Yeah. Yeah. In our experiment, we actually saw that when you're trying to predict, let's say, how a map looks like based on current observations, having some language input helps a lot.
Yeah.
Because the language can give you, some spatial cues along with semantic cues of where things are. And so, yeah, so I was wondering whether you guys are thinking along the same line.
Yeah, so to some degree, I'd like to learn more about your work. If you want to shoot me an email with it or something, that would be great.
Sure, yeah, great.
Hi, Stefanie. Thanks for your awesome talk. I'm a little confused with a detail in your talk. That is, when you are
Can you get closer to the microphone? I can't hear too well.
Okay. Thanks. When you are transfer the English sentence to RTL formula, you said you prefer the positive sentence. That is, for example, the negative sentence, just like avoid to a place, just like this. So I'm confused why you are preferring the positive sentence. So because even though the negative format that can also be expressed by a RTL formula.
People preferred to use the positive sentence. So this is just what our annotators did. Like we would show them we'd show them a pair of trajectories, and they would and annotate that pair with avoid the yellow room. They would instead give the positive variant of that, like go through the blue room. I can maybe
Okay.
That's just what they did. I think people are more positive than negative, I guess.
Yeah. So in this corpus, maybe some commands are actually equivalent, right?
Yeah. Well, yeah. So if this is an example here where go to the green room and avoid the yellow room.
Yeah.
Or maybe this one's, yeah. Go to the green room and avoid the yellow room, right? So the first example, where it goes, they would say, go to the green room and go through the blue room. And they're both legit, like they both match the trajectories, but they correspond to different LTL expressions. So in our newer work, it's robust to this. So in this work, we were annotating English with LTL, and if the English didn't correspond to the LTL, it was a problem because then it would learn the wrong model. On the other hand, with our more recent work, where we're learning trajectory from only trajectories, the algorithm is robust, so it's able to figure out whether they use positive or negative, as long as the trajectories are correct and match the language. It's able to learn.
I see. Thanks.
Yep.
Okay, I have a question. First of all, thank you very much for the really great talk, Stephanie. I really enjoyed the overall framework of the human-robot collaborative MDP, collaborative POMDP. It was a really nice way to tie everything together. So one kind of high-level question I had was, it looks like in a lot of the work that you spoke about, language is kind of an input at the beginning of an episode. It kind of commands the robot to do something, and then that specifies the task for the robot, if you will. It specifies a reward function that is then kind of the thing that the robot must learn to optimize or must plan to optimize. But in the human-robot collaborative POMDP, language could be actually input at any given time. It could be potentially conditioned on what the robot is doing wrong currently, how to correct it. Have you thought about how to integrate it?
Yeah, a little. We have some older work where it does take language input continuously in a really simplified domain, and we have some newer work that isn't published yet where we're sort of also using a more dialogue POMDP model. The dialogue community, there's a dialogue community that does human-computer dialogue, and they use POMDPs. They use a POMDP framework where the human can give input with language kind of all the way along. And then there's like a state machine representation with slot filling. So what you're trying to, what the system is typically trying to figure out is like, where am I in this process, and then what slot am I filling based on where I am. So for example, if I'm booking an airline flight, where am I in the process, and if I'm in the telling me my information, am I telling the system the source, the destination, the start date, the round trip, all that stuff. So it's this very structured representation. It's not more open-ended and compositional like LTL. So like where I think that thread is going to end up is by having a connection between the LTL state representation and dialogue, where you can ask questions about the LTL expressions, except people don't want to talk about LTL. So you're going to have to either go from LTL back to English. So you can say I think you mean this, is that right? Or we've also been thinking about showing them trajectories. So if you have 5, this is with Ankit Shah, who's our postdoc. If you have 5 trajectories that you think it might, or 5 LTL expressions you think it might be, you can essentially use a stat solver to say, show me a trajectory that differentiates between 2 of the LTL expressions, that works for one and fails for another. And then show the person that trajectory and say, is this okay? And if they say yes, then you've eliminated some of the expressions.
Okay. Yeah.
Make sense?
We
haven't done that yet, but I definitely want to do that. And I would point to the dialogue community as an example of actually one of the biggest practical successes of POMDP so far is in natural language dialogue. So a lot of what we've been doing is bringing it back to sensing and perception and stuff.
Yeah, and in this context, you could even potentially, it's not just a dialogue purely in language. The language could actually be conditioned on what the robot has currently done. It's not that everything must be resolved at the beginning of the.
Yeah, totally. Absolutely. Yep. Yeah, we just make that assumption a lot to focus on other stuff, but I totally agree. It's assumption, it's wrong. And I would love to relax it. And it would be really cool to do that.
Awesome. Yeah, thank you. I actually have another question that I wanted to quickly, if no one else has a question, and do we have time?
We are a few minutes over.
Okay, all right. In that case, maybe I'll just shoot an email instead.
Okay, there's one question in the chat too, but we're over time. I'll do it quick if that's okay.
Yeah.
So does POMDP assume the observation space is factored by objects as well? Can it handle faulty object detection? Yeah, actually, that's what it's all about. So we assume that the detector is noisy, so it can have false positives, it can have false negatives, and then so we can decide to look more than once, essentially, to smooth out that noise, and also, of course, based on the range of the detector. That's what it's all about. Okay. Thank you very much. I'm sorry I can't visit in person. Hopefully someday soon. And if anybody has questions or wants to meet up, please shoot me an email, and we can do that.
Yeah, thank you for having this great talk, and we'd definitely love to have you